She guessed correctly that I was asked to talk about atmospheric escape and mass loss, a pretty broad topic at the summer school. And because it is a huge topic and because we all want to have lunch at noon, I and I'm sure you only want to hear me talk for that long, although I love talking about atmospheric escape. I had to narrow down this beautiful, large topic. Oh, no, sorry. There we go. Into a somewhat more manageable chunk of planets. So what do I mean? So when we look at this, I'm sure you've seen this plot many times, but when we look at this amazing figure of exoplanets that have been discovered here as a function of orbital period and size, there are actually several features in this figure that are most likely shaped by atmospheric escape and mass loss. For example, this, okay, I'm trying to be good, it's difficult. So this area here, the reason that it's empty is probably not because planets can't form there or we can't find them, because we can easily detect these planets here, but it is most likely because atmospheric loss has actually eaten away these planets and made them much, much smaller and shrank them here. But I'm going to not talk about why this area of this diagram is empty. Instead, I'm going to be focusing on the smaller planets, which are the most abundant planets that we've discovered today and that are typically smaller than Neptune, but often a little bit bigger than Earth. And we call them super Earth and sub-Neptune. So that's the part of the phase space I'm going to talk about, and I'm going to focus on the mass loss for those planets, although there's mass loss shaping many other planets in this diagram. So these super Earth and sub-Neptunes have been, for somebody who tries to understand the formation of planets and has for a long time sort of only really had the solar system to play with, have been a real surprise and real fun, because they are so different, right? What we have on the solar system. In the solar system, we have Earth, and then we have nothing, and then we have Neptune. And all these planets are sort of in between their size. And so when we look at the same sort of planet size, this is going to be hard, planet size, orbital period, a diagram, and split this up again, you see there is structure here. All these points that look like one big blob on the previous diagram, if you look a little bit more closely, you really do see two populations emerge. So this upper chunk here is what we typically call sub-Neptunes. And these planets down here is what is now commonly referred to as super Earths. And we see them divided in two populations, not only sort of in the planet size or the period space, but also if you look at them in sort of a planet size stellar mass space, you still see sort of two separate chunks. Furthermore, there is a subset. So for most of these planets, we only have their radius and their orbital period because they come from transit observations. But for some of them, we also have mass measurements. And so you can play these fun games, right? You can now, when you have a radius and a mass, now you can calculate a bulk density. So you can either put them on plots like this. You can ask what planet, for a given planet mass and radius, where does it fall? And you can infer something about its composition, or you can just simply calculate its bulk density, but it itself already will tell you something about what the interior of this planet could be. And what we typically find is that planets that are smaller, roughly than sort of 1.6, 1.8 Earth radii, tend to be in bulk composition very similar to Earth, so roughly 5 or 5.5 gram per centimeter cube, so consistent with sort of being a rocky planet. Whereas planets larger than that are less dense than that, and typically best explained with having sort of some light gas on top, and the best candidate for that is hydrogen and helium. So the very first question then is, so we have all these planets, how did they form? Should we think of these super Earths and sub-Neptunes as two distinct populations that were born separately and in their own unique way, or did they form as one and evolve into those two populations? And so before we can talk about mass loss, we need to talk about gas accretion, right? We learned about clouds just now and how to map the 3D structure of atmospheres. But I'm going to tell you how you get any of these atmospheres to study in the first place before we can do anything with them, lose them, study them, whatever you like. So to get any gas, to accrete any gas, if you are a growing little planet in the disk, the first thing that you need to do is you need to be big enough that your gravity is strong enough that it can hold on to any of the gas particles that are whizzing by. And so this condition basically means that the physical, your Bondi radius, which is basically the distance from a body where the escape velocity from the thermal speed from the gas molecules equals the escape velocity from the body itself, it has to fall outside your physical radius, right? Because the gas molecule, the atmosphere has to sit on top of you. You're not a black hole where it can be inside you. So your Bondi radius, you have to be big enough so your Bondi radius is larger than the physical radius of your growing planetary embryo. And just as a fun sort of exercise, if you calculate this for sort of a 1 AU distance in the Minimal Stellar Nebula, that's roughly the size of Ceres, our largest asteroid, right? Roughly to say 200 kilometers or so. This is how big you have to be that you could start holding on to some gas gravitationally if you're sitting in the disk. Okay, that's good. So now you can start capturing some of those gas or hold on to it gravitationally and start to accrete an atmosphere. But if you then just ask the simple question, say, I grew a core of a few Earth masses, how big of an atmosphere can I hold on to in the scenario? You will find it's much less than 1%, only typically 0.1 or less of 1%. So to really get a substantial atmosphere that can sort of double yourself in size, which is what we find from these exoplanets, you need to accrete at least a percent or a few percent of hydrogen and helium. So what happens next? So the next stage in my growth process actually involves a little bit of cooling. So now I have this gas accreted. It's gravitationally stuck to me in my Bondi radius and my Hill sphere. Now I wait a little bit and gas will cool and contract with time. And now, because I have cooled and contracted a little bit, I can stick on more gas on the outside. So this initial growth phase of accreting an envelope is actually done by cooling. So one of my colleagues has termed this very nicely. It's accretion by cooling, or to cool is to accrete. So you have to wait a little bit in time, and then you can accrete another layer of gas on top. And this is why this first initial stage of accreting a few percent of an hydrogen helium dominant envelope actually takes quite a bit of time because it's regulated by the cooling. This is also why when you calculate sort of the expected, envelope mass fractions, this, where F is the expected envelope mass fraction, why it doesn't strongly depend, for example, on the gas disk density that you have. It doesn't show up here in this expression because you're not supply limited, you're cooling limited. So it will depend on the opacity you have because that regulates how quickly you can cool, and the disk lifetime because it tells you how many cooling time scales you have to do the accretion, right? The longer your disk is around, the more cooling time scales you have, the more gas you can accrete. And you can also understand, for example, why it get almost a linear scaling with core mass, with the initial mass you have of the embryo that's doing the accretion, because the more massive you are, the bigger is your Bondi radius, the bigger is the reach over which you can accrete the gas. But nonetheless, with this pretty simple understanding, you can show that you can accrete a couple of percent for typical disk lifetimes for these typical masses we find of a couple of Earth masses around other planets. So we could say, great, we are done at least with the growing part, success. But it turns out that you don't get to keep all the gas you just accreted. And this is because while you're doing the accretion and the gas is around, right, your outer boundary condition, the edge of your Bondi radius, if you wish, is pressure supported from the disk that you're accreting from. So if your gas disk goes away, and if it does it fast enough, it's usually quite rapid. The gas lifetimes are long compared to the gas dispersal times. If the gas dissipates rapidly compared to the cooling and contraction time of the envelope, the outer layers basically get lost because they will expand almost into vacuum, right? If you remove the gas on the outside, what was before pressure confined will just expand and be lost from your planet. And this is what we call spontaneous mass loss. Another group called it boil-off, but this is the same thing. So it's this spontaneous boil-off mass loss that you undergo as the gas disk goes away. And it's quite significant. You lose typically between 25 to 70% of all the gas you just accreted. It has an interesting side effect because you're sort of blowing off the outer layers and it takes away some energy. The inner part of the envelope that remains actually cools and contracts quite rapidly, much faster if you would have done if you hadn't included this boil-off phase. The good news, though, is you still can declare victory, and you end up with a couple of percent in mass of an envelope, of a hydrogen-helium envelope, on top of these cores. So you can sort of explain why the typical sub-Neptune can be well explained with a couple of percent hydrogen and helium sitting on top of a, say 4 Earth mass core. So far, no mass loss, or a little bit of mass loss, spontaneous mass loss. And now you have formed planets that are a few core radii in size, and you still don't get to keep all the envelope. Some of them do. So if you're really massive and far away from the star, you may get to keep most of it at this point. But for a lot of planets, there is significant subsequent evolution. And this actually, there are not only from one end, there's actually 2 mass loss mechanisms that both appear to drive the evolution of this exoplanet population. And so let me explain the 2. So the first is related directly to the way that the planet has formed. Because the planet accretes gas from the disk onto its core, this core never had a chance to really cool to very low temperatures. So once you have accreted your envelope, you basically have an interior of the planet that wants to cool, right? Even Uranus and Neptune today have interior temperatures of thousands of Kelvin. And that wants to cool, and that that will basically inflate the envelope or keep it inflated for longer periods of time. At the same time, you're heating the outer layers of this planet from the bolometric luminosity of the star, and you can drive a Parker type outflow this way, and that's what we term core-powered mass loss. At the same time, you also are bathing the very upper layers of the envelope of the planet in EUV and XUV radiation from the young stars that deposits energy high up in the atmosphere that will also drive a hydrodynamic outflow. So although the energy sources, if you wish, that's powering the outflow are different between the 2 mechanisms, they both give you a hydrodynamic outflow. And this is one of the reasons, I think, why the broad brush results that you infer from them across the whole exoplanet population are very similar. There are some subtle differences in terms of the time scales on which they operate. Most of the EUV and XUV radiation should lead to mass loss early on within sort of the first 100 to 200 million years, whereas this outflow will be slower because it's the bolometric luminosity that sets the sound speed at the sonic radius, if you wish. So it's so it should last more like half a year to a giga-year to sort of turn a sub-Neptune into a super-Earth. But I would like to stress, nature doesn't have to choose between the 2. They're almost certainly operating together, and we have actually started doing some detailed work combining them, and that's essentially what we find. But I'll spare you the details. You can come and find me afterwards if you really care. All that matters for this talk is that these planets are undergoing this additional mass loss. And so over time, although we initially start out with a population that all lives up here, or up here, so they are basically used to consider a population that all look like sub-Neptunes, that with time you actually start forming these super-Earths, because you basically strip these sub-Neptunes of their envelopes, and you can basically, just with mass loss, get a very good match to the observations that show this sort of bimodal distribution, these 2 populations of sub-Neptunes and super-Earths. So one of the take-home messages and big surprises for me has been that it really looks like that these planets that look like 2 distinct populations today, sort of rocky, bulk composition type super Earths and sort of sub-Neptunes that tend to have sort of a few percent of hydrogen helium in their envelopes really have formed as one and evolved into being these two populations. And we not only have sort of evidence for this from sort of a modeling on population level point, looking at the radius period and radius stellar mass plots. But in addition, we, let me actually skip this. In addition, we can actually see the planet populations change in time. So, right, so in our solar system, planet formation was basically over at 100 million years, right? Moon forming impact happened, definitely the gas giants formed is done. Nothing, I mean, little things happened, nothing major happened. But what we are finding, what we're predicting, and finding for the exoplanet population, that you're really still changing and birthing, if you wish, super Earths from sub-Neptunes on timescales from 100 million to gigayears. And this is exactly what different groups have been finding observationally, that if you, for example, of course, we can't just look at a system for a gigayear and watch what happens, right? But luckily, we have many systems. So if we look at a large sample of different ages, what emerges is that, for example, the ratio of super Earths to sub-Neptunes changes as you go from a younger population, which is here in green, to an older population of stars. So it suggests that you're making new super Earths, probably from the sub-Neptunes, on this time scale, which to me is really amazing. We can sort of indirectly see planet formation happening. So I think this is one other population level evidence that this mass loss is really happening. It's not just in our models, it's not just in our wishful thinking. We sort of see signatures on it on sort of a population level picture. In addition, we of course can also observe it. It has been observed for several individual systems, which is super interesting. But I will take Peter Gao's advice, and just for simplicity and for the purpose of this talk, I will stick to the population level view, because you know, planets are very diverse and there'll be loads of details and interesting systems. But this is sort of like a zero order, broad brush stroke looking at this population. Okay, so in addition to that, I thought I also wanted, so there are many interesting things about mass loss we can talk about. There's, for example, also really interesting signatures of this mass loss on the super Earths, right? These leftover planets, once they are super Earths, what are the leftover signatures that mass loss happened maybe in the interiors and individual atmospheres? But I will not talk about this here, but I'm happy to discuss with you afterwards. But I thought one really more general point that I would like to make, and I think that's important for people to think about, is the effect of mass loss on the mass radius distribution. So I showed you earlier a plot of mass and radius that sort of lets you infer something about the composition on your planet. And here I think is one really nice example. So what we have here is a mass and radius plot, basically for planets around M dwarfs. And there was this very intriguing result that, so first of all, let's see what we look here. Here, this is the sort of Earth-like composition line, and this is where we see sort of these, I would say, standard super Earths lying. And then there's this population here of what I just called before sub-Neptunes, right? But curiously, they seem to lie quite nicely on this blue line here, which happened to coincide with what you would get if you would make a planet 50% water and 50% rock iron by composition. And so one interpretation of this data then was, well, maybe we discovered a population of what's called water worlds. And it's a very poorly defined term. So just for this purpose, I will use the most extreme version. Now, when I say water world, I only mean planets that have 50% water. I think it's much more nuanced, but just so these very extreme groups of planets. So it seems to fall quite nicely on this. And the argument was that basically if you draw hydrogen composition lines on this, say 1%, an Earth-like composition and 1% hydrogen, you should get these bananas here, or you would expect your planets to find on these bananas And that doesn't seem sort of a nice fit to the data. And so there are several, I think, important lessons here, or cautionary tales for us to take away. So the first is that if you want to compare a population of planets to sort of a composition, if you are dealing with hydrogen or a gas, you have to worry about the thermal evolution. You cannot pick just a certain random entropy, because the entropy will change as a function of time, because your planet will cool and contract, and mass loss will further change your entropy. So that's the first lesson. The second is that the amount of atmosphere you expect for a planet to have after formation, I already showed you that the accretion depends on planet mass, right? How much you accrete, but also how much loose depends on planet mass. So if you start out with a population of super Earths, or like sub-Neptunes with hydrogen helium envelopes, and you let it evolve in time, here you have atmospheric mass fraction as a function of core mass. And this is the same planets here plotted in planet size as a function of planet mass. So if you evolve this in time, you'll see, most importantly, so you get these super Earths being born, these are the strip planets, and you'll see that the amount of atmospheric mass fraction left over is not constant per planet mass, but it scales with planet mass quite strongly. So you would not expect one constant mass fraction in a planet of planet mass. And it pretty much falls on a pretty narrow line. This was only for one specific temperature. So of course you should do this for a proper distribution of M dwarfs. But you will see these lines are very different from sort of these banana curves that would be the default models that you would get if you just assumed a hydrogen envelope of a certain temperature and entropy, which is not the right description for gas evolving in time and undergoing mass loss. So these are now the results properly for an M dwarf population with the right sort of temperature distribution and insolation fluxes. And so you see that you get actually a relatively tight clustering, but with some scatter, of course. And so if you now go back and compare this with this very nice sample of M dwarfs that we just looked at before, you do see that there is still this degeneracy. Basically, this blue line is the 50% water line of these water worlds, and the orange line is the average, most densely clustered line that you would expect for planets that were born in the disk, were rocky on the interiors, accreted hydrogen helium envelopes, and then underwent mass loss and thermal evolution over sort of a few giga-year timescales. So we are still stuck with this degeneracy that we cannot just use masses and radius alone to uniquely determine their interior composition. But so whatever you do when you do modeling and trying to infer bulk compositions of planets, or especially of sub-Neptunes, when you want to do models with hydrogen, please account for the thermal evolution, and please do account for atmospheric mass loss. So let me conclude. I think the three main points that I would like to leave you with is atmospheric mass loss plays an active role in shaping the small exoplanet population today. We actually see it happening right now for some systems, and we have strong evidence of it happening throughout their evolution, which I think is really quite different from what we have known about the solar system and its planets. Atmospheric mass loss and thermal evolution really need to be accounted for when modeling the mass radius relation for sub-Neptunes, right? This is really an important point, because otherwise you will get the wrong results. You infer the incorrect atmospheric mass fractions, and you may think that you can break some degeneracy between, say, a water world and some hydrogen and helium envelopes when you really haven't. And this is really different, right? If you were only modeling planets that are pure rock, say, it's okay. You don't have to worry about that the rock has been sitting in the universe for a giga-year. It will have changed, right? The Earth hasn't changed size significantly, not on the scale that we're talking about here, since its formation. So it's very different if you're dealing with gases, right? So just remember that whenever you're dealing with gases, you have to worry about both the stellar insolation, and the thermal evolution. And if you do have mass loss, that will also significantly modify your entropy. And last but not least, I think on a broad population level, we have really strong evidence observationally, and when you tie this to modeling, that the majority of super Earths really were born with hydrogen helium envelopes, and then that were then subsequently lost, and that their interior bulk densities, this is just one number, are surprisingly consistent with that of Earth. So with that, I'll stop here, and I'm happy to take any questions.
Hi, Hilke. Thank you for the beautiful talk. My question is, so you mentioned very briefly that these two mechanisms, the corporate mass loss and photo-evaporation, they can act together. Do you expect one to dominate the other at some time scale of the planetary evolution?
Yeah, that's a great question. We are actively writing a paper summarizing what we found, but basically to zero order, yes, there is both a time slice in which one mechanism seems to dominate or the other, but there's also, broadly speaking, what we find is that core-powered mass loss seem to be dominant for lower mass, hotter planets, and photo-evaporation seems to be the dominant mechanism for more massive, cooler planets. But they do enhance each other, so you can get more mass loss than you would expect it by itself. And we really we should have a paper at least on the archive very soon, and I'm happy to talk about it more. But yeah, I think we will be able to disentangle this, and you can even show, I think, that the super Earths we see, they consist a significant fraction of that population was most likely stripped by core-powered mass loss, and a significant fraction of that population by photo-evaporation. And then there is also a part that probably had both of them acting together. Yeah, so anyways.
Hi, Hilke. Thank you for the great talk. So I understand that the photon gap looks a little different for M stars. Is that a sharp discontinuity as a function of host star type? And also, could you comment on the overlap between the list of planets that we can characterize atmospheres on, which will skew towards small stars, versus targets that will tell us the most about the classic photon gap?
Sorry, can you just start with the first part of your question? I missed the key part.
I get that the photon gap around M stars look a little different. Is that a sharp discontinuity as a function of host star type? Or does it lie in a continuum as you go from K to M stars?
Yeah, so to us at this moment, it looks more like a continuous evolution, and I think it can still be explained to zero order well with mass loss, although it's possible that there are additional planets in there. We're trying to quantify that right now, so I don't have a conclusive evidence yet, but it does look different. But I would say to zero order, large difference really can just be attributed to how the mass loss mechanisms scale with stellar type. But nonetheless, I think there may be a hint of something more there.
So if you do have a sub-Neptune that has a non-trivial amount of volatiles in it, so like an actual Neptune, and it goes through these evolutions, you're losing the hydrogen. What happens to the water as this is going? Are you going to dissociate the water and oxidize your rock and lose the water too, or are you going to keep the water?
Great question. I think from the work that we have done and that I've seen in the literature, from what we understand right now is I think to zero order, it depends where your water is. If your water is mostly in the atmosphere, and that's if it's not trapped inside your planet, it actually easily is lost with a hydrogen, because the outflow, both in core-powered mass loss and photo-evaporation, typically is so fast that it can easily drag other species with it. So if the atmosphere is well coupled, if the water is well coupled with the rest of the hydrogen dominant atmosphere, I think you will lose most of it. You can keep a little bit at the end when these hydrodynamic mass loss limits break down, but it's often at the very end, and it's relatively small amounts of water. Now it depends. If you just need a few oceans worth, you can probably keep that. But if you're talking about 1% or so, and you think it was coupled with the atmosphere, the expectation is that you would lose it. Yeah.
So we have an online question. It's asking, during the thermal evolution period of the planet, the star also evolves in billion or million year timescales. How would this impact the mass loss of the planet?
Oh, great question. It depends on your star. FGK stars evolve, of course, much less than, for example, M dwarfs, but we have done some work accounting for the luminosity evolution, for example, of M dwarfs. And so, yeah, you can account for that and integrate over that. And so it basically can change both the rates and also in photo-evaporation, depending on your activity and activity history. But you can account for that, and you can actually even you can show that the first order of the models are consistent, and you can even sort of turn the question around and infer something about the stellar activity history using some of those mass loss results. But yes, definitely true.